This video will be looking at analysis of differentiable ranking and sorting operators. The structure of the video will be as such. First, an introduction to understand the problem and the relevance of fast rank and sort. Then, we analyze fast rank and sort to gain an intuitive understanding of how ranking and sorting can be expressed as linear operators and use regularization to flatten the kinks to make it differentiable. And in turn, expressing the problem as a projection onto a permutahedron. Then, we'll look into experiments and their results, followed by criticism and conclusion. So first, an introduction. The current implementation of sorting and ranking is non-differentiable. Furthermore, they have the potential of being incorporated into useful objective functions. As such, the current ranking and sorting functions cannot be used in end-to-end machine learning models as the objective function for gradient-based algorithms. The current solutions to tackle these problems are also either too niche, where they cannot be extended to other types of problems, or they run too slowly, which is detrimental given the large datasets which are common in today's context. As such, we look into a fast rank and sort, which is a differentiable proxy for ranking and sorting, which takes big O n log n in time and big O in n in space complexity. This algorithm is first introduced in Blondel in 2020. To understand the projection onto the permutahedron, we first look at what is a permutahedron. A permutahedron is a convex hull of a doubly stochastic matrix, where its n factorial vertices are n by n permutation matrices. Furthermore, the optimal solution of a linear program will be at the vertex, making it a permutation matrix itself. Next, we'll define the sorting and ranking problem. First, we let theta be a random vector to be sorted. We then let the permutation be represented by sigma, and the inverse of a permutation is the corresponding inverse sigma inverse. The arcsort of theta would then be denoted as sigma theta, where each value is smaller than the previous, and hence the sorted vector is represented by theta, which is arranged by the arcsort. Accordingly, the ranked vector is equivalent to sigma inverse theta. Now, we will express ranking and sorting as linear operators. The sorted vector can be expressed as a vector multiplication with a permutation matrix. Next, we see that when multiplied with a reverse permutation matrix, P transpose P theta is maximum when the projection matrix P sorts theta in ascending order. As such, sorting can then be casted as finding a permutation matrix that satisfies the following criteria. Hence, sorting and ranking problems can now be expressed as a collection of linear programs. By regularizing the operators with a strongly convex function as such, the problem can then be casted as a Euclidean projection onto a permutahedron. This form of regularization has shown to be differentiable. Now with the algorithm, we'll look at some experimental results. The time complexity test shows that the algorithm runs fast even for large tensors, where a tensor of length 100 million runs in around a minute. In the top K classification loss test, we see that the performance of the soft top K model is comparable to that of the classical cross entropy loss. A takeaway is that to achieve the maximum effectiveness and performance of these soft rank based operators actually require problem-specific tuning for them to perform optimally. Lastly, for the Spearman ranks correlation test, we see that a majority of models using the soft rank layer outperforms those without. This is especially so when given more time to train. We see that when increasing the number of epochs from 100 to 200, the number of models that outperforms a simple linear model goes from 4 to 9 out of 14. However, one criticism is that the error of sorting is unbounded. In this example, a tensor consisting of two entries, 0 and x, is sorted, where x is varied. We see that the error is unbounded, as it increases linearly when x is greater than 1. This error can then be large enough such that the output is virtually unsorted. In conclusion, this method uses a regularization technique that is applicable to different types of problems, and the resulting operator is useful for ranking and sorting based machine learning models that requires larger datasets. This is as long as shortcomings are factored in to prevent vulnerability from unsorted errors, as well as problem-specific tuning to achieve the maximum performance possible.